Michael and I were recently in a Pinewood Derby race where we won grand champion with this car. When we showed up, people were actually laughing at it. They looked at this car and thought, what a joke. But believe it or not, it won grand champion and, to the best of my knowledge, is the only car that has ever broken 3.5 seconds on the track that we raced. In this video, we're going to cover how we built this car and the physics and engineering that went behind it to turn such a simple looking car into a grand champion Pinewood Derby.
Fast.
Oh, wow. Okay, we just got the other one with a 3, 4, 9. And Michael's smoking again. How do we do?
3508.
Okay, here we go again. 3 in a row. What do you think of that?
Is there any possibility I can get all of you with your...
When Michael and I started to prepare for this race, we started by first reviewing the physics and engineering that would go into making a good Pinewood Derby car, and then we worked backwards. And as a parent, I would recommend all parents out there to use this opportunity as a way to teach your children some basic physics, engineering, and mathematics. If you boil it down, a Pinewood Derby is nothing more than a very, very fun experiment in the conservation of energy. In this video, we're going to cover the basics of the physics and engineering behind a Pinewood Derby. We're going to cover potential energy, kinetic energy, friction, rotational momentum, and how do you control for an error. Okay, the first concept we're going to cover is potential energy, and this is probably the most important concept covered in this video. Potential energy is stored energy. Basically, the higher something goes, the more energy it has stored in it. All objects fall at 9.8 meters per second squared, so the higher you go, the longer it'll have to accelerate. You want to see an interesting video on this? Google NASA hammer feather video. And what it does is it shows an astronaut on the moon where there's no friction dropping a feather and a hammer at the same time. And what you'll see is both the feather and the hammer fall at the same rate of speed and they both hit the moon at the same time. So that's a real interesting lesson on turning potential into kinetic energy and the rate of acceleration in a vacuum. Now, how does this apply to your Pinewood Derby car? Well, the point is, the higher you go, the more energy you get. In this car, its center of gravity, where it balances, is approximately about 1.5 inches from the very back of the car. On a normal Pinewood Derby car, you have the axles in a little bit. Their center of gravity isn't way back here, it's about right here. So if you draw a little triangle, because it's on an angle, you'll see that this car has about a full inch or more drop in the race itself. So how did we do it? We took a normal Pinewood Derby car with a center of gravity about right here. We cut it right down here, spun the ends around, and we moved the axles all the way out to the very end. By doing that, we were able to move the center of gravity from here all the way back to just in front of the rear wheels. And on an angle, that gave us about another inch or so drop in the race. Okay. The second concept is kinetic energy. Once we build the potential energy, taking it up as high as we can, we then convert it from potential to kinetic energy. Kinetic is the energy of motion. Now, as I mentioned, in a friction-free world, okay, every bit of energy that is potential will be converted to kinetic and accelerate the object. That's the ideal. The problem is, we don't live in an ideal world and we're not having a Pinewood Derby race on the moon. We have to deal with two other problems: friction and rotational momentum. And that's what we'll cover next. All right, well, we just covered building the potential energy. In an ideal world of zero friction, what we would want to do is we would want to take this potential energy and move it to what, Michael?
Kinetic?
Kinetic energy. And kinetic energy is the energy of motion. Once again, if you watch the YouTube video, NASA feather hammer video, you'll see that on the moon, if you drop a feather and a hammer at the same time in a frictionless world, they both will fall at the same speed. If we were having a Pinewood Derby race on the moon and we dropped everyone's Pinewood Derby car at the same time, they would all hit the ground at the same time. There would be no winners and losers. The problem is, with the Pinewood Derby, you have friction. You have friction because it's going to be touching that railing, plus it's not falling straight, it's falling at an angle. So what happens is we don't get 100% of the potential energy being converted to kinetic energy. We have a large amount of the potential being converted to kinetic energy, but we also have some energy being lost to friction and some energy lost to rotational momentum. The key is to minimize these two blocks and to maximize the amount of kinetic energy. Now we're going to cover how to do that. The next concept we're covering is friction. And what friction is friction is the enemy of kinetic energy. Take two blocks together and rub them together, they get very hot. That is kinetic energy being wasted on friction. Anytime you deal with friction, think about two flat surfaces meeting themselves. That maximizes friction. Here's an example of basically a cone-shaped object. If I use this end, the broad end, I am having a lot of surface area meeting each other. Okay? I have this much surface area. To cut it down, you use the pointed end towards the rubbing surface, and what you just did was you reduced the amount of friction of surface on surface. So anytime two surfaces touch, think about wasting kinetic energy. Right, Michael?
Yeah.
Now, how did we get rid of all all that friction? What Michael and I did was we took a look at the car and we detailed every single surface on surface and try to reduce the friction. The first one we did were the wheels. If you take a look at the wheels, there are multiple points of friction. One, where the nail touches the wheel. Two, where the wheel touches the track. And three, where the side of the wheel touches the rail. In order to cut down the amount of friction of the wheel touching the rail, we put a slight angle in the wheel. We filed off some of this outer edge. That reduces the amount of surface that will be touching the rail when it bumps into it. What I've labeled G, that means graphite. We graphited everything. Graphite is a lubricant that cuts down on friction. The second thing we did was there is a surface on the head of the nail that touches the wheel. The nail goes in here, and so you have a flat surface against a flat surface. We put a slight angle in the back of the head of the nail to make sure that there's very little surface of the nail that touched the wheel. The other thing we did was on the side of the wheel, it has lettering. We filed off all the lettering to make it very smooth, and we put graphite on the outside of the wheel so that once again, as it hit the rail, it would be lubricated. As far as the nails go through the axle of the wheel, or the hub of the wheel. What we did was we found out where the nail touches the wheel, and we used very fine sandpaper to buff off as much as we could. So we made this extremely smooth, and we put graphite on it. The last thing we did was we put the nail through the car wheel, put it on the drill, and we ran it. And so we ran this thing to make sure that any type of friction that exists between the nail and the inner part of the wheel would be buffed off, smoothed out, and we poured graphite in there right before the race to make sure that this thing was full of nothing but graphite and the nail. That greatly reduced the surface areas that touched, and the graphite lubricated everything that could possibly be touched. Okay, now we're on the last little bugger. Okay, Michael, what is this?
Potential.
Potential energy, and we want to convert it as much potential energy into what?
Kinetic.
Kinetic energy. And what are the two energy stealers? What is this?
The friction
Friction
and rotational.
Rotational momentum. Okay, now what does that mean? If you want to see a good demonstration of this, it's basically a flywheel demonstration. We have 4 basic flywheels on the car called wheels, and we have to get them to start rotating. That takes energy. If you want to see an interesting YouTube video on it, search gravity-defying flywheel. It's pretty interesting. Well, on this situation, the only real way you can cut down on that is, one, reducing the weight of the wheel. And what we did was we did file off some of the wheel to make it smoother and to make sure that there's angles on the surfaces. But 2, some people lift one of the wheels off the track, so when it goes down, it only has 3 wheels touching to minimize the rotational energy required to get this thing moving. One thing you be sure to do is review the rules of your race. Some races will allow you to do 3 wheels, others won't. Some will allow you to polish the wheels, other ones won't. So before you do anything, make sure you read the rules and apply which ones are allowed for your particular race. All right, we're going to cover 2 last little concepts, not necessarily conservation of energy concepts, but concepts that work into the race. Michael, the shortest distance between two points is what?
A straight line.
A straight line, right? How does that apply to a Pinewood Derby race? Well, if you watch a Pinewood Derby race, what you'll see is when the cars come down there, they juggle a little bit, okay? They jump around, okay? That's wasting basically time, because the longer the car travels, the longer the race is going to take. One way we address that is we took the wheels and we wanted to make sure, if you listen, there's a little bit of a flutter to that wheel. In order to try to minimize that, we put an index card between the wheel and the car, pushed it in as far as we could, glued it, and then pulled the index card out, so there's a very small gap between the wheel and the car. But once again, we made sure that there's a very little surface area touching between those two, and we graphited it very well. The other one that I thought was really interesting was that if you just have 4 set wheels, it's impossible to really control every factor and know what it's going to go. Because for one, when they put the car up there, you don't know if it's going to be a slight angle. What that did was some of the engineers that came up with this concept said, okay, we accept that there's going to be an error in this race. We can't control for the flow if the car is left alone. Right? We don't know how it's going to be put up on the top. We don't know how it's going to drop and things like that. There are too many variables. So what they did was, if they basically came up with the concept that if you have a known error, why don't we just simply accept that there's going to be an error and correct for it? So what some people do, we did not do this, you can take one of the wheels and have a very slight angle on it. And what that does is it accepts that your car is going to drift a little bit, but it's going to drift and ride the rail down. Now, typically you don't want to ride the rail, you want to stay away from it. But what some people believe is riding the rail, giving up a little bit of friction for riding the rail, overcompensates for the fact that the car's floating down like that. That was kind of an interesting concept. We did not do it, but you may want to try it. I would recommend making sure there's very little float on your wheel by using that index card principle. The other concept, once again, this is a car that floats. If you measure out that distance, velocity is time over distance. To maximize the distance, you're going to lower your velocity. You want to go straight line. So with this slight angle, okay, you're basically going to take this car and ride this rail down, but have the angle at such a slight amount that it takes a long time before it turns all the way over to hit the rail. The last concept is aerodynamics. We save this one for last because it doesn't mean a whole heck of a lot in the Pinewood Derby, but most kids really focus on that. Some kids spend an unbelievable amount of time building these really cool looking cars, really aerodynamic, and they lose. We built something that looks like a piece of garbage and we won. Okay? We didn't focus on aerodynamics. The only aerodynamics we really focused on was there's a slight wedge here in the front. It's nothing more than a very thin piece of wood. Okay? If you want to have some fun, you can create your own wind tunnel, get a little piece of incense or something that smokes, have a small fan blowing the air over it, and what you'd see is the smoke would smoothly go across here. You'd probably have some eddies here, and you'd probably have some eddies back here, which is turbulence, but it's not going to be enough to really slow down the car. Most of the time you're going to shoot exactly for 5 ounces, which is what this did. You want to have that weight back there. And 5 ounces on something this big, aerodynamics doesn't mean a whole heck of a lot. But other than that, those are the concepts. It's a conservation of energy. You want to maximize the amount of potential energy, and you want to be able to maximize the conversion of potential energy to kinetic energy. You want to minimize friction. You want to minimize rotational momentum, and you want to correct for the errors of riding the rail or that jiggle. And I wouldn't focus too much on aerodynamics. Michael, Brick King, you have anything else to say about it?
No, just listen to this and you'll probably win.
Like, share, subscribe, and comment. Okay, and once again, this card wouldn't take very much time at all. It's those simple concepts that result in winning. And we want to stress again, make sure you understand the rules of your particular race. Some races won't allow you to do some of the things that we did, others will. Other than that, let's sign out. What do you think?
I like it. I think you'll win if you do all of this stuff. Like, share, subscribe, and comment.
Later, peeps.
Goodbye.